Section: Introduction. In this section, we explore the effectiveness of large capacity models such as large language models, LLMs, and large multimodal models, LMMs, in various domains and tasks. Scaling up these models by increasing the parameter count can improve performance. However, dense models, which use all parameters to process inputs, face challenges due to their large size, leading to slower inference speed. Sparse mixtures of experts, SMoE, offer a promising solution by incorporating parallel neural networks, experts, that are selectively activated for specific input tokens, enhancing efficiency. While dense models like GS-hard can scale up to 600B parameters with lower training costs than smaller dense models, SMoE models like 8x7B have shown superior performance compared to other large models. Despite its success, SMoE has limitations such as low expert activation and a lack of fine-grained analytical capabilities. These issues hinder the model's effectiveness and scalability, especially when dealing with a large number of experts. To address these challenges, we introduce multi-head mixture of experts, MH-MoE. This approach splits each input token into multiple subtokens using a multi-head mechanism and assigns them to different experts, leading to denser expert activation without increasing computational complexity. By distributing subtokens to various experts, MH-MoE can focus on different representation spaces simultaneously, enabling a more detailed understanding of both visual and language patterns. MH-MoE offers several advantages, including higher expert activation and better scalability. By optimizing almost all experts, it can achieve a 90.71% activation rate, allowing for more efficient model capacity scaling. The multi-head mechanism also enhances the model's ability to capture semantically rich information from diverse experts, leading to a finer-grained understanding. Additionally, MH-MoE's straightforward implementation and compatibility with existing optimization methods make it easy to integrate into models like GS-hard for improved performance. We evaluate MH-MoE across three settings: English-focused language modeling, multilingual language modeling, and masked multimodality modeling. Our experiments demonstrate the effectiveness of MH-MoE in enhancing model performance across these tasks. Section Summary. In this section, we explore the challenges faced by sparse mixtures of experts, SMoE, models, such as low expert activation and limitations in analytical capabilities due to tokenization patterns. To address these issues, we introduce multi-head mixture of experts, MH-MoE, which splits input tokens into subtokens and distributes them to different experts for denser activation without increasing computational complexity. MH-MoE enhances expert activation, improves scalability, and enables a finer-grained understanding of information from various representation spaces, showcasing its effectiveness across different language and vision tasks. Section: Background. In this section, we will discuss the sparse mixture of experts, SMoE, model and its routing mechanism, as well as introduce the MH-MoE method. SMoE enhances model capacity without increasing computational demand, leading to improved performance in deep learning tasks. Unlike densely activated models, SMoE consists of multiple independent feed-forward networks, FFN, as experts in each layer, along with a gating function to determine the weights assigned to each expert's output based on the input token's hidden representation. The routing mechanism in SMoE typically involves selecting the top k experts from a total of n experts, where k is usually less than n. Larger values of k tend to enhance model performance but can also reduce training efficiency. To address this issue, we introduce MH-MoE, which densifies expert activation without increasing computational complexity. MH-MoE employs a multi-head mechanism to split input tokens into subtokens and route them to different experts for denser activation and deeper understanding. Each layer in MH-MoE contains a set of experts, and the input tokens are processed through a multi-head layer before being split into subtokens. These subtokens are then routed to specific experts based on gating values, and only the top k experts are activated. The outputs from these activated experts are merged back together to form the final output of the layer. By implementing token splitting and merging operations, MH-MoE effectively increases the data volume routed to each expert, leading to denser expert activation and improved model performance. The model's ability to capture semantic information from diverse feature spaces across experts is enhanced, without introducing additional computational costs. MH-MoE is designed to be simple to implement and can be easily integrated with existing SMoE frameworks for enhanced performance. Section Summary. In this section, we introduce sparse mixture of experts, SMoE, as a key advancement in deep learning, enhancing model capacity without increasing computational demand. We propose MH-MoE, a method that employs a multi-head mechanism to achieve denser expert activation and deeper understanding by splitting tokens into subtokens and routing them to various experts. By implementing token splitting merging (TSM) operations, we efficiently increase data volume routed to experts, enabling a finer-grained understanding by capturing semantic information from diverse feature spaces. Section: Training Objectives. In this section, we outline the training objectives of MH-MoE. Our goal is to minimize both the loss related to the main task and an additional load balancing loss simultaneously. The load balancing loss addresses the issue of uneven distribution of workload among experts. By considering a subset of subtokens and the frequency at which they are assigned to different experts, we calculate the load balancing loss. This loss is determined by the number of experts, the total subtokens in the subset, and the gating function that decides which expert a subtoken is routed to. The task-specific loss, denoted as L_text task, depends on the specific task that MH-MoE is learning. For example, during pre-training, we use a language modeling loss where the model predicts the next word in a sequence. The overall objective is to minimize a combination of the task-specific loss and the load balancing loss, with a coefficient alpha controlling the balance between the two. Moving on to the experiments, we first describe the setup we used. We compare MH-MoE with two baseline models, dense, which is a transformer decoder without sparse parallel modules, and SMoE, which is based on a previous approach. Our MH-MoE builds upon SMoE with similar settings to ensure a fair comparison. We pre-train all models on the same data and ensure that the parameter count of MH-MoE is either the same or lower than that of SMoE. We then discuss the pre-training data used for MH-MoE, which includes experiments in English, multilingual, and multimodal domains. These experiments involve pre-training on various datasets using tasks like predicting the next word in a sequence. The model architecture and hyperparameters are based on SMoE, with different configurations for language modeling and multimodal tasks. The pre-training duration and hardware setup are also provided for each task. We evaluate the models using perplexity, analyzing the validation perplexity curves under different expert settings. The results show that MH-MoE consistently outperforms the baselines in terms of learning efficiency and language representation across various pre-training scenarios. The lower perplexity values of MH-MoE indicate its effectiveness in learning and the benefits of incorporating more experts for improved representation learning. Section Summary. In this section, we aim to simultaneously minimize the loss associated with the target task and an auxiliary load balancing loss in MH-MoE. The load balancing loss is computed based on the subtoken set and the frequency of subtokens routed to different experts, while the task-specific loss depends on the particular task the model is designed for, such as language modeling during pre-training. Section: Downstream Evaluation. In this section, we conduct downstream evaluations for each pre-training task to confirm the effectiveness of MH-MoE. For English-focused language modeling, we assess our models on 9 different zero-shot benchmarks to evaluate their performance in various natural language tasks. Comparing SMoE with the dense model, we observe significant improvement with SMoE, showing that models like SMoE benefit from a larger model capacity. Overall, MH-MoE performs the best across all benchmarks, with an average performance gain of 1.1 for 8 experts and 1.5 for 32 experts compared to SMoE, showcasing the effectiveness of our multi-head mechanism in modeling English-focused language. For multilingual language modeling, we evaluate our models on the Cross-Lingual Natural Language Inference (XNLI) corpus across 14 languages. MH-MoE outperforms SMoE, demonstrating consistent gains on downstream tasks and the effectiveness of our multi-head mechanism in modeling cross-lingual natural language. In masked multimodal modeling, we evaluate our models on vision language understanding and generation benchmarks. MH-MoE excels in tasks like visual question answering, visual reasoning, and image captioning, surpassing both dense and SMoE models by significant margins. These results highlight the enhanced visual information comprehension of SMoE and validate the effectiveness of our multi-head mechanism in capturing diverse semantic and detailed information within visual data. In our ablation studies, we analyze the functionality of MH-MoE through experiments adjusting the number of heads and examining the impact of different components. We find that as the number of heads increases, there is an initial performance improvement followed by a decline, suggesting an optimal range for the number of heads. Additionally, we observe that incorporating both the multi-layer perceptron (MLP) layers and token splitting merging (TSM) operation is crucial for enhancing model performance, with each component playing a unique role in improving the effectiveness of MH-MoE. Moreover, we find that a single-layer MLP is sufficient for token segmentation and fusion, indicating that increasing the number of MLP layers beyond one has minimal impact on model performance. Section Summary. In this section, we conduct downstream evaluations for different pre-training tasks to validate the effectiveness of MH-MoE. For English-focused language modeling, our MH-MoE outperforms SMoE and dense models across various natural language tasks, showcasing the benefits of the multi-head mechanism. Additionally, in multilingual language modeling and masked multimodal modeling, MH-MoE consistently demonstrates superior performance compared to SMoE and dense models, emphasizing the effectiveness of our proposed multi-head mechanism in capturing diverse semantic information in both English and cross-lingual contexts. Section: Experts Activation Analysis. In this section, we examine the activation patterns of experts in SMoE and MH-MoE. We notice that SMoE has a more uneven distribution of expert activation, with many remaining inactive. On the other hand, MH-MoE shows a more balanced activation of its experts, addressing the issue of underutilized experts. Moreover, as we increase the number of heads in MH-MoE, the frequency of expert activation also increases. When we scale up the number of experts from 8 to 256 for both SMoE and MH-MoE, we observe that MH-MoE outperforms SMoE in utilizing experts effectively, leading to better performance. This scalability advantage allows MH-MoE to improve the upper bound of expert utilization from 64 to 256, showcasing its effectiveness in downstream tasks. Our model excels in various tasks for both languages and images, thanks to its multi-head mechanism. We conduct a detailed analysis to show how MH-MoE captures intricate semantic information, such as polysemous words and rich semantic areas. By routing subtokens to a greater number of experts, MH-MoE effectively models polysemous and false cognates words in languages and enhances semantic understanding in images. In our analysis, we compare the divergence levels of subtokens from polysemous words to non-polysemous words in languages. The results indicate that polysemous words route their subtokens to more experts, capturing diverse semantic information. For images, we observe that MH-MoE routes tokens from complex texture regions to a wider range of experts during training, improving semantic understanding. We also conduct a complexity and parameter analysis for SMoE and MH-MoE to show that MH-MoE has lower computational and parameter costs compared to SMoE in all experimental settings. Detailed parameter counts for all experiments and models can be found in the table provided.